Hi folks, welcome to the Math 611B Chapter 6 Concept Roundup. We're looking at basic integration here. If you look in the video description below, you'll find that the video is time-stamped by topic. There's also a downloadable copy of a review with work solutions and a downloadable copy of the notes. Let's start by looking at the definite integral in terms of area. So integrals are related to the area between a curve and the x-axis. If a curve is totally above the x-axis, then the area and the definite integral are the same thing. The definite integral is written like this, and I'll make it a little bigger so that you can see it. Okay, it has boundaries, a and b. Those are left and right boundaries, typically, or beginning and ending. In order to find a definite integral, we require f of x to be continuous over the interval ab. Now here's the rub. Area below the x-axis is counted negatively toward the definite integral. So you could think about the definite integral as net area. Okay, it's stuff above the x-axis minus stuff below the x-axis. And that has an application in net change. There's a reason that we want this property. So if we look at this function that's down here, kind of silly looking thing, we want to find the definite integral from 0 to 3. Well, I'm really just wondering how many blocks there are. So here's one full one, two full ones, three full ones. Oh, and now I've got a triangle. And that triangle has a height of 3 and a base of 2. So its area is half base times height. Or this is an area of 3. So in total, in this space in here, I have 3 full blocks and then 3 more from the triangle. So I have 6 square units in terms of area. When I write down the definite integral, I do not write the units squared. All right, let's check out the next part. We've got this area down here. Well, that's a semicircle with a radius of 2. So a semicircle with a radius of 2. Let's see. A circle with a radius 2 would have this area, pi r squared. Since it's a semicircle, it's only half of that. But notice here that it is area below the x-axis. So it's going to be negative when we're talking about our integral. This works out to a half times pi times 4, or negative 2 pi. But again, in terms of area, this would be 2 pi units squared, if we just look at the area. The integral from 0 to 7 would be this part counted positively, and then this part counted negatively. That's a pi, or 6 minus 2 pi. There's a subtle distinction here. If we wanted the area, for some reason, we just wanted to find the total area bounded by the curve in the x-axis, it would be 6 units squared plus the 2 pi units squared, or 6 plus 2 pi units squared. I would talk about units squared if I were asked for area specifically. I would not if I were asked for the integral, but it has an application to area. Okay? So if you're talking about area in particular, everything's positive. If you're talking about the integral, the definite integral, stuff above the x-axis is counted positively. Stuff below the x-axis is counted negatively. Now we're going to take a look at a few definite integral properties. So the first one is the integral from a to a. That means, say you've got a curve like this, you're looking at the area from a to a. That's going to be 0 every time. If there is no width, meaning there's no interval from a to the next point, there is no area. Okay, the next property. If we have the integral from a to b of k, where k is some constant, then that can be rewritten this way if it's more convenient. You can pop that k out front. And we had a rule that was similar to this with differentiation. We had the constant multiple rule. Well, same thing here. You can pop that constant out front and then deal with the function separately and multiply by the constant at the end. Okay, the next property. The integral from b to a is just the negative of the integral from a to b of f of x dx. So changing the order of boundaries just changes the sign of the integral. And we'll see why later on in the video when we do the algebraic versions of definite integrals and the fundamental theorem of calculus. The next one. If we have the integral of some function plus or minus another function, that is the same as the integral of one function plus or minus the integral of another. And it's catchy when you say it. The integral of a sum is the sum of the integrals. That just means you can split these apart if you want. Notice the boundaries don't change. The same if you have differences, if you have a minus between them. And then finally, this one we actually used on the last page, but we didn't deal with it formally. If you have an integral that goes from a to b, and then you pick up and do from b to c. Well, let's think about that. Let's imagine a curve that happens to be all above the x-axis. This first part here would be equivalent to this area. This next part would be equivalent to this area. And what would you have in total? Well, if you add those two areas together, you would have the integral from a to c. If there is sort of a stop point in between that they both come to, then you can combine them into a single integral. This holds where a is less than b is less than c, meaning b is in between. On some interval a to c. So let's try and put some of those to use in a few examples. Let's suppose that we don't know anything about these curves f and g. We just know that the integral from 1 to 3 on f is 7. The integral from 3 to 6 is -2 on f. So the net amount of area is going to be more below the x-axis. On g of x, we know that from 1 to 3, it's 3. And from 3 to 6, it's -3. And then we're asked to find the integral from 1 to 3 of f of x minus g of x. So we're going to put these properties to use. We said the sum of an integral is the same as, the integral of sums is the same as the sum of integrals or differences. Well, what this means is you can split this apart. It's the integral from 1 to 3 of f minus the integral from 1 to 3 of g. And the integral from 1 to 3 of f was in green up there, minus the integral from 1 to 3 on g, that was in black. So in total it gives us 4. That's our final answer. We use some of those properties. The next one, we've got the integral from 3 to 1 on f. Well, that's not up there anywhere, but we could rewrite it. We know if you switch the boundaries, you turn the whole integral negative. And that's something we know about. The integral from 1 to 3 is 7. So this is going to give us -7. And maybe this would be a little less abstract if we had the curves, but there's a good reason to do it without the curves so that we can really isolate these properties. C, the integral from 3 to 6 on g. Well, we know something about that up in blue in the top right. But we've got this pesky 5. And our rule was you can pop a constant out front. So this is going to be 5 times the integral from 3 to 6 on g. That's -3. For a final answer of -15. Next one, we've got an integral from 1 to 6 on g. Okay, that's not up above, but we've got that black one and we've got the blue one. And notice how there's a 3 here and a 3 here. You can combine these. This was the last of the integral properties on the last page. The integral from 1 to 3 plus the integral from 3 to 6 is the same as the integral from 1 to 6. So now I can just put them together. 3 plus negative 3. And on this one, it happens to work out to be 0. Meaning, from 1 to 6, there's an equal amount of area above the x-axis and below the x-axis. Very last one, we've got the integral from 3 to 3 on f. There's no width. If these are the same, then the integral will always be 0. Now we'll take a look at indefinite integrals. And an indefinite integral is just an integral without boundaries. And we'll bridge the gap between what that means graphically, what we've been doing up to now, and what it means algebraically, which we're about to do. We'll bridge that gap in the last piece where we do the fundamental theorem of calculus. So the basic idea here is the integral of some function is this big F, which is the antiderivative of little f. And an antiderivative means the simplest function that differentiates to f, little f. And we're very good at differentiation by this point. And then we have this plus c business. And the reason we need that is that when you differentiate, there actually could be any constant tacked on the end, because it will turn into a 0 when you differentiate. So this constant that appears when we integrate is called, predictably, the constant of integration. Okay. And it is often unknown. Or we would have to have some extra piece of information to be able to figure it out in a specific case. So down here we have common antiderivatives. Here are all our f's, here are all our big F's. Those would be the antiderivatives. And then some less common antiderivatives. You can notice that these are all just the differentiation rules in reverse. And as things get a little more involved, a really good approach when you're doing an indefinite integral is just to make a reasonable guess at the integral and check by differentiating. If you're not quite right, if your coefficient is off by a little bit, just correct by multiplying or dividing by a certain amount. Now, there are a few of these that are really worth knowing. I'm going to zero in on this one and these ones. So x to the n, when we differentiate, we know that the power would go down by 1, and the old power comes down front. Well, when we integrate, it says x to the n turns into 1 over n plus 1, x to the n plus 1. Sometimes people write that as x to the n plus 1 over n plus 1. Either is good. They obviously mean the same thing. But here's what's happening. So let's decode this. It means power goes up by 1. The reciprocal, or flip, of the new power goes out front. So, for example, if you had x to the 3, it would anti-differentiate into power goes up by 1, flip of the new power goes out front. You're not sure? Well, check. If you differentiate that, okay, so in this one we were anti-differentiating. If we go the other way and we differentiate, well, we'll get 1/4 times 4x cubed, or x cubed. We will have undone it. So it must work out. And it can work with rational powers. The only power you can't use this for is an n of -1. Okay. And if you have n of -1, a power of -1, then we have this situation up here. 1 over x turns into ln of the absolute value of x. The other ones are our basic trig functions. And one way to organize the trig derivatives and antiderivatives is to set them up in a circle. We know that sine x differentiates to cos x. And cos x differentiates to negative sine x. And it follows, therefore, that negative sine x differentiates to negative cos x. And then the whole thing just goes around and around. If we go in this order, then we're differentiating. But if you want to anti-differentiate, then it's pretty straightforward. You just go in the opposite direction. So rather than having to remember any rules, anti-differentiate, can spell, there we go. We just have to go counterclockwise in this circle. So cos x anti-differentiates to sine x. And obviously, sine x differentiates to cos x. So we can just set up that wheel, and it should help us out. Every time that I integrate something, I'm going to check by differentiation. So let's find each indefinite integral. Over here, I'm going to do it as if I had no insight. I'll just use the rule. So a 3 is going to stay out front. And x squared, the power is going to go up by 1. And the flip of the new power comes out front. Minus the integral of x. Well, power goes up by 1. Flip of the new power goes out front. 2, well, the thing that differentiates to 2 is 2x. And there could be some constant. So there's a constant of integration there. Gives us x cubed minus a half x squared plus 2x plus c. Check by differentiating on some scrap paper. Does this get you back to this statement up here? Okay, so what's it going to give us? I'm not going to write equals. I'll just write that it goes to 3x squared minus a half times 2x plus 2. And of course, the derivative of the constant is 0. So that's 3x squared minus x plus 2. Is that what we started with? Ah, yes. We're feeling pretty good here. We must have done it properly. We should note that this is the actual answer. Okay. Everything in green, that was just a check. Let's check out the next one with the wheel o trig. Very exciting. Okay, differentiate, that is clockwise. Anti-differentiate is counterclockwise. So sine x anti-differentiates to negative cos x plus c. Now we'll check. So let's see. If I differentiate negative cos x, it's going to give me negative. Derivative of cos x is negative sine x. And the derivative of c is 0. Gives me sine x. Great. We did it properly. This is our final answer. Now, things can start to get pesky when you have coefficients with the x. And we can set up a bunch of rules for how to deal with that. Or we can just differentiate or attempt to anti-differentiate and then check. So I'm a big fan of the latter approach. I'm a big fan of as few rules as possible. But of course, you can come up with rules here. So the antiderivative of sine, we already showed, was negative cos x. And so here it's going to be a 3x. And I'm just making a guess. Is that right? Let's find out. I'm going to check. If I differentiate that, I'll have negative sine 3x. And then from the chain rule, I'll have another 3. So it's going to give me 3 sine 3x. And that's when I stop and think about this. I go, ooh, too big by a factor of 3. How can I fix that? The fact that it's too big, it's 3 times too big. And the way you can fix it is by putting a third out front. So I'll go back up here to the negative cos x, and I'll put that 1/3. And let's see what happens. If I check now, I'd have negative 1/3 times negative sine 3x times 3. Or I'd have a negative, I'd have positive rather, when I'm through, 1/3 times 3 sine 3x, or just sine 3x. It works out when we differentiate. Okay. The other way that you could conceptualize it is, when you have a coefficient of x, the reciprocal of that coefficient is going to end up out front. It may not be the only thing that ends up out front, but it'll be part of what ends up out front. But either way, we should check by differentiating. So now we're sure this must be right. Negative 1/3 cos of 3x plus c. Let's try another similar one. We've got e to the 2x minus 1. So again, I'm going to guess that, well, e to the x integrates to e to the x plus c. So this is going to be e to the 2x minus 1 plus c. I'm not that confident, so I'm going to write a question mark. I'm going to make sure I get rid of that question mark before my teacher sees it. Check. Well, if you check this, you'll get e to the 2x minus 1, and then from the chain rule, times 2. Oh dear. Too big by a factor of 2. Fix it with a half. Okay. And we can check that, and it will indeed work out. One last one. We have 2x to the 4 minus 3x plus 5 over x. Now, sometimes people find those 5 over x's tricky to think about. So I'm going to rewrite it this way. Plus 5 times 1 over x. So that I hopefully won't miss the fact that there's a 1 over x involved. And if we go back to our common antiderivatives, 1 over x, or a power of negative 1 on x, that is the special case. That anti-differentiates to ln of the absolute value of x. And the reason that it's absolute value of x is that 1 over x exists for negative numbers as well. So its antiderivative needs to as well. Let's see what happens. When we anti-differentiate, I'm not going to guess and test here. I'm just going to say that's 2 times x to the 4, power goes up by 1, flip of the new power in front. Minus 3 times power goes up by 1, flip of the new power in front, plus 5 times ln of the absolute value of x. And I also need to squeeze in a plus c. And through the magic of technology, we can. Okay, let's just figure out what that becomes. 2/5 x to the 5th minus 3 over 2 x squared plus 5 ln of the absolute value of x plus c. As per usual, we're going to check. I feel pretty confident about this one, though. Check. We'd have 2/5 times the derivative of x to the 5, which is 5x4, minus 3 over 2, derivative of x squared is 2x, plus 5 times the derivative of ln x, which is 1 over x, and the derivative of c is 0. or 2x to the fourth minus 3x plus 5 over x. Come on, big money. Is that what we started with? Ah, yes. So we're feeling great about this. That must be our indefinite integral. From there, we've got some cases where we can find the value of c. So if some point on the integrated function is known, we can find the value of c. Let's check out this one. We know that the derivative is 2 plus cos x. And on the original, on f at pi over 2 is 3. Meaning f of x contains the point pi over 2, 3. Okay. And at this point, we're assuming we're working in radians. Find f of x. So if I want to go up a step, up to f, what I'm doing is integrating. If you want to go down, then you differentiate. So let's see. What is the indefinite integral of f prime going to be? It will be 2 becomes a 2x. Oh, cos x. Come on, circle of trig. I really don't need any more than that. Obviously, the integral of cos x is sine x. Plus c. And up to now, that's been all we can say. But here we know if you substitute in pi over 2 for x, you should get 3 for y. So let's do that. We're going to sub the point pi over 2, 3. 3 is our y value. Pi over 2 is our x value. Let's see what that gives us. 3 equals pi plus sine pi over 2. By now we know that that is 1. I'm going to figure out what c is. So I'll subtract 1 from each side, and I'll also subtract pi from each side. So c is 2 minus pi, meaning that the actual function must be 2x plus sine x. That's a plus sine x. Plus that c value, which turned out to be exactly 2 minus pi, or roughly negative 1.14. But that's only possible if you know some point on the integrated function. The last thing we'll look at with indefinite integrals is drawing the antiderivative. So there's one big idea, and if you're clear on the big idea, then this is going to go okay. F of x describes the slope of big F at every point. Because f of x is the derivative of big F. Okay, so it's going to describe the point. So let's take that and let's catalog what we know about slope on this function over here. Right now, all we're told is that when we sketch big F at 0 is 0. So it starts at the origin. Okay, and I'm going to do a whole bunch of description before I go ahead and try and sketch this. So here are the things I know. The slope starts off being negative. Not because this function is pointing down, the black function is pointing down, but because it's at negative y values. It has negative slope to start with. Right here it has its lowest negative slope, so it's going to be steepest. Over this whole interval, slope is negative. And what does that mean? If slope is negative, then a curve is decreasing. So f is decreasing. big F is decreasing. Okay, now what happens next? Well, over the next section, the slope becomes positive. So over this entire region, slope is positive, which means F, big F, is increasing. Now there are still special spots that are happening. Right here, slope is 0. So that means that we're going from a decreasing slope to an increasing slope. Let me draw that. Decreasing slope to an increasing. This must be a minimum value. Few other important points. Right over here, slope is at a maximum. So this is going to be steepest in terms of its positive. And right here to end with, very small positive slope. That means almost 0. And a slope of 0 means horizontal. Okay, so those are like your Lego instructions for how to build this antiderivative curve. Now we just have to follow them. So I'm going to start at that origin because it told me to start at the origin. And I have a negative slope, and it gets steeper. And now it's going to get less and less steep until it gets to a slope of 0. Okay? There's the rough contour. Now, I don't have any scale on my y-axis there. I don't know how steep it's supposed to be. It doesn't matter how far down I went, but I'm showing the right features. It got steepest at 1, and it got a slope of 0 at 3, at x equals 3. Now it's going to have a positive slope, and that positive slope gets to its steepest at 5. And then that positive slope gets less and less, and closer to horizontal. Now notice I have no idea where that horizontal asymptote is going to end up in terms of the y-axis. But I have this basic shape. Decreases, gets steeper, then gets less steep, hits a minimum value at 3, has its steepest positive slope at 5, and ends with a slope that is nearly 0. That's the best way that I can suggest to graph these things. And if you went ahead and took the green one and tried to draw its derivative, you would end up with something that looks like the black one. So again, you could check here, but it's a little more abstract when we do it in the context of not having any algebra. Okay, finally, definite integrals with algebra, aka the second part of the fundamental theorem of calculus. So this is what we've been working up to. The integral from a to b on f of x is big F at b minus big F at a. There are different notations that different texts will use. Sometimes that's called big F from a to b, or some texts will only use the right side bracket for that. They're all equivalent. This is the big idea. So if you want to find that sort of net area idea, then you need to find the antiderivative, and you need to sub in the upper boundary minus the lower boundary. The thing that ties this together with differential calculus is that the derivative of big F is little f. In other words, big F is the antiderivative of little f. Okay, so we've got the integral from 2 to 5 of 3x squared minus 2x. Let's put this to work. So we know that we have to antidifferentiate. We don't need any of the plus c's, and that's because we'd have plus the plus c minus the plus c. They'd disappear when we went through this process here. Okay, so we'll antidifferentiate. The antiderivative of 3x squared is going to be, if I wanted to do it step by step, I'd say that it's this, and then the other one's going to be minus a half x squared. I think 2 times a half x squared. I think that here we can probably do it by inspection. This is going to be x cubed minus x squared. Okay, I'm having pangs of doubt, so I'll just check by differentiation. Let's see, x cubed is 3x squared if I differentiate, minus 2x. Oh yeah, we must have integrated properly, or anti-differentiated properly. Okay, so this function right here, that's our big F. And what we're going to do is we're going to take big F at 5 and subtract big F at 2. The antiderivative at 5 minus the antiderivative at 2. Let's see what happens. That's 5 cubed minus 5 squared. That's the big F at 5. Minus 2 cubed minus 2 squared. That's the big F at 2. I work that through. That's 125 minus 25 minus 8 minus 4, or 100 minus 4 gives us 96 without having to draw anything. Let's try it for the next one, which is very similar. It's actually the same function. So we know that its antiderivative is x cubed minus x squared. We're dealing with, in this case, from 5 to 2. And graphically, this is hard for us to think about. But we just need to think upper boundary is 2, lower boundary is 5 here. We sub it in. Big F at 2 minus big F at 5. Okay, let's see what happens. That's going to be 2 cubed minus 2 squared minus 5 cubed minus 5 squared. Just subbing into that red function. 8 minus 4, so that's 4. Minus 125 minus 25, that's 100. Whole thing gives us negative 96. Now look, those answers are really similar, and that shouldn't surprise us at all. A lot earlier we looked at definite integral properties, and we said if you switch the boundaries, then the sign of the integral will change. So here we have no surprise. Surprise. Since the integral from 5 to 2 on some function should be the negative of the integral from 2 to 5. Okay? And we can see that happened. Just got negativified. So we could have saved ourselves some work, but I wanted to illustrate that. And you can see why that happens. Instead of having f at 5 minus f at 2, now you switch the order. When you switch the order in subtraction, the sign changes. We'll try a couple of other ones here. Let's integrate. So e to the 2x is going to become e to the 2x. Now let me just try that out. If I differentiate, that'll become e to the 2x times 2, or 2 e to the 2x. Oh dear, that's too big by a factor of 2. I need a half out front. Or you could reason that out because there's a 2 in front of the x. All right, again, we've got wheel o trig. Cos x anti-differentiates to sin x. And that's from 0 to pi. And we're going to deal in exact values here. So I'll sub it in. This here, that's our f of x. We'll do f at pi, and I'll color code this, minus f at 0. And then f at 0 is not necessarily 0. And these are big F's. Okay, equals, well, that'll be 1/2 e to the 2 pi plus the sine of pi minus big F at 0. And you could have used rounded brackets if you prefer. 1/2 e to the 2 times 0, that's just 0, plus the sine of 0. Okay, let's see what that works out to be. 1/2 e to the 2 pi plus sine pi. Sine pi is just 0. Minus 1/2 e to the 0. E to the 0 is 1. So that would just be 1/2. And sine of 0 is 0. And there's the exact value of our answer. We'll do one last definite integral, and then one little application problem. So again, I'm going to anti-differentiate here. So that's going to give me 3 times 1/2 x squared minus 5 over x. That's like 5 times 1 over x. So its antiderivative is going to be ln of the absolute value of x. Now I'm going to clean this up right away. That's 3 over 2 x squared. Off to the side, I'll check that. If I differentiate this whole thing, what will I get? I'll get 3 over 2 times 2x minus 5 times 1 over x. Or 3x minus 5 over x. Ah, we must have done it perfectly. It differentiates to what we started with. So now, I'm going to sub in that 2, and then I'm going to sub in that 1. So, big F at 2 minus big F at 1. I'm giving up on my color coding here because we've done this a bunch of times. So 3 over 2 times 2 squared minus 5 ln absolute value of 2 is just 2 minus 3 over 2 times 1 squared minus 5 ln, again, absolute value of 1 is just 1. We'll work this out. That's 3 over 2 times 4, which would be 6, minus 5 ln 2, minus 3 over 2 times 1 squared, that's just 3 over 2, minus 5 ln 1. Ln 1 is just 0. Okay, the log, any base of 1 is going to be 0. So now we have 6 minus 5 ln 2 minus 3 over 2. Combine, that's 9 over 2 minus 5 ln 2. Or if you prefer, 4.5 minus 5 ln 2. Okay. Now you could give that in a decimal version, but look, it looks so pretty here in exact terms. Okay, last thing we'll look at is finding a boundary. So this is just setting up a definite integral question, but hiding the unknown somewhere different. So let's suppose that we have a function 2x minus 1. Looks like this. And the integral from 2 to something is 10. We just want to find what that something is. Now, I think it's obvious that there's going to be a k value out here that is going to give us an area of 10. What we may or may not realize is that there might be another one, but the algebra will take care of it for us. So let's see what happens. It's saying the integral from 2 to k on this function is 10. Okay. Well, we'll just do our regular stuff. We'll anti-differentiate 2x minus 1, so that's x squared minus x. The boundaries are 2 and k. And the whole thing's equal to 10. Now that's big F at k minus big F at 2. Really, nothing has changed here. I'm just thinking about that. So let me plug those in. That will give me k squared minus k minus 2 squared minus 2 equals 10. Or k squared minus k minus, let's see, this thing here is 4 minus 2, so that's minus 2. Ooh, it's a quadratic. We love quadratics. Let's go ahead and solve. That's k minus 4, k plus 3 equals 0. So the k values should be 4 and negative 3. Now that negative 3 seems really weird. It seems like if we went between negative 3 and 2, we should end up with more area below the x-axis than above. But the order of the boundaries is important. So at a certain point, we want to give up on the whole geometric interpretation because the idea of right to left and left to right starts to hurt our brains. Let me just take my calculator and check these integrals, see if they all work. So if k is 4 and k is negative 3, that's what we're saying as answers. Hopefully they'll work out. My calculator has a definite integral button on it. Yours might too, in which case you probably won't be allowed to use it. Okay, so we're saying that the integral from 2 to 4, or maybe you will be able to use it, and we just need to come up with questions that are more analytical in nature. 2x minus 1 dx. Okay, if I sub in 4 for k, will this work out? Yes, it gives us 10. Now, that one didn't surprise us. Let's try it the other way around. If I do the definite integral from 2 up to negative 3, that's weird, but it does have meaning. 2x minus 1 dx. Will this give us 10? Yes, it will. So those solutions are appropriate. And you didn't need to check with the calculator. They're going to work out because the algebra worked out. I hope that you found this at least somewhat helpful. There is a review down below, so feel free to take a look at that and at the worked solutions. Take care. See you next time.